Okay, sorry. I'll start. Yeah. So I'll be presenting parallel IO on BIT1, which is undergoing development in the Plasma-PEPSC project in collaboration with many institutions. And why the need arose for having parallel IO, well, I will show soon. And this is a teaser to the next presentation of my colleague Jeremy, who will present in-depth analysis of parallel IO profiling. So what the profiling which I'm showing, it's his work, and this is just a part of it. Originally, BIT1 has had a serial IO, which means each MPI rank will write to disk in a separate file. With increasing number of MPI ranks, this can become a bottleneck for HPCs. This means that the IO handling will, let's say, suffocate the HPC. So to overcome this, we have to use parallel IO. And how does parallel IO work? It can communicate between MPI ranks through memory, and only some rank, only a few ranks, then write to disk. And the number of files then can be reduced significantly, and this can bring improvement. So BIT1 has so-called dump files, which save the phase space to disk so that it can continue the simulation from the last saved state, but has also diagnostic files, which can be toggled on by activating slow one or movie files. And they can be around 10 files per MPI rank. So if you scale up to, let's say, thousands of MPI ranks, then it can be tens of thousands of files. In the case of movie file, this builds up every movie step. So parallel IO is needed in order to be able to use more MPI ranks, much more like exascale situations. So this write throughput plot has been produced by my colleague Jeremy, and you can see here 200 nodes. And each node has maybe around 100 CPUs. So this is like 20,000 MPI ranks. And we can see that after a certain number of nodes, the write throughput is throttling, so it goes down because there are too many files to be written on disk. And this has been tested on multiple machines. So multiple HPCs, Discoverer, Dardel, and Vega in this plot. So there's, let's say, an optimum write throughput for serial IO, which is maybe around 40 nodes. And if we want to use much more, then we have to use parallel IO. So let's say the version of BIT1 using parallel IO, we nicknamed it for now improved BIT1. And the dump files and the diagnostic files will now be saved in so-called binary pack. And this binary pack is a feature of the ADIOS2 library. ADIOS2 stands for Adaptive Input Output. something. And this ADIOS2 is actually a backend for the OpenPMD library that we are using in this development. OpenPMD is Open Particle and Mesh Data. So it's a standard that aims to standardize a way of writing PIC data or simulation data in a way that can be used by multiple visualization tools, and your data will look the same in all of them. And this particle and mesh data standard it appends metadata to your data. So you don't just save data in binary, but can also append units, normalization factors, so that okay. Mikhail? Yes.
Oh, sorry, I just had the mic open. I'm a bit late for today.
Sorry. Yes. So what have we implemented so far in BIT1 is parallel write and parallel read. The parallel write can write to disk, and we call this checkpointing. And format to use is binary PEG4, which is the format with the highest write throughput. It optimizes write throughput to disk. There are other binary PEG formats with their own pros and cons. So feel free to check out the ADIOS2 library for these details. But we can also write in memory, and this is called streaming, which means we'll pass the data directly to our plotting software, bypassing the writing to disk. And this is useful, for example, for debugging, when we don't want to save to disk and then read to disk to see what's going on. So we just pass through memory and we see on the fly what is happening in the simulation. But also it's useful when the writing to disk is limiting the simulation, or when in some cases, in some production cases, this can happen if the data is huge. In all reality, the parallel I/O actually decouples from the simulation. So they actually run in parallel. The simulation doesn't wait to write to disk, but if the next iteration for saving to disk arrives before the previous one finishes writing to disk, then this buffer will be overwritten, so we can have corrupted data. So in certain situations, maybe you want to use memory write. In others, you want to disk. Writing to disk actually for BIT1 is quite fast because it's not a huge amount of data. And with nowadays technology, this is not actually a problem. To read with parallel I/O, we can read from disk, and it's called restored from checkpoint, or read from memory. And this is the, let's say, the in-situ visualization. And when we read from disk, let's say we have an extra option, which is load balancing, which is actually a very primitive routine for load balancing. It is not very optimal for high number of MPI ranks, but for demonstration purposes, for now, it's good, but it's work in progress. So this will be fixed. here it's a profiling made by my colleague Jeremy, which is the write throughput comparison between the serial original I/O of BIT1 and the parallel. So the original serial is in blue, and the parallel I/O is in green, and on the y-axis is the writing speed. And with increasing number of nodes, you can see that the parallel I/O is much faster than the serial I/O, and it doesn't saturate as early. But of course, we will do more testing to increase number of nodes and to see if this saturation actually happens, say for 200 nodes or not. But you can see the difference between serial and parallel I/O. And where does the speed come from? The parallel I/O reduces the so-called metadata, which is actually a large amount of data. So this metadata here. Mind the y-axis is normalized to the size to the runtime. So it's in percent. So if you sum up how much it takes to write the same data using serial I/O compared to parallel I/O, you see that the amount of time has been reduced dramatically, and this so the same amount of data is transferred in much less time, and this is the write throughput that you see on the first graph. So the metadata has been reduced, let's say, by 99.9%, and the writing time has been reduced by 99%, let's say, approximately. How do we implement this parallel I/O in the code? We have to create a series object where we put the file name and extension. So, and when we write the extension, then the library already knows how to save the data. We can choose not only binary pack, we can also choose HDF5, but it will not be as fast as binary pack 4. This is the fastest format. In this series, we can attach some constants that we can use later in our plotting scripts, for example, number of species, some scaling information, and we have our main loop where we save the data, and we actually here append the buffers to be saved, and we call flush, and all the data is being written at once to disk, maximizing the write throughput. All data will be in a big binary pack, and this will be saved to disk at once. And of course, after we flush data, then we close the iteration. And at this point, this iteration cannot be opened again. So, and it's you go to the next one. And then you close your series. So this is, say, the main code. But inside the save function, the data is prepared in vectors. So this is a C++ library. BIT1 is C, but of course, you can compile with a C++ compiler and have the same thing. So you extract the data like you have it, and you push it in a vector. This is a local vector, which it will be clear at every saving iteration. But of course, if you have multiple data, then all these vectors have to be pushed in, let's say, global vector, so that when you exit the function, you don't lose the data. So this global function will actually hold all the data until we call flush. And of course, we clear the local vector. So we create such an iteration, we open it. We have to specify the data type, which in case is always float. The library needs to know the global extent of the data. So if it's data which is uniformly distributed across MPI ranks, you just multiply the local size of the number of ranks. But if this is not the case, then you have to use MPI reduce, let's say, to get the global size of the whole data. Global means all the ranks together. And of course, we have specified the local extent of the data for this MPI rank and offset in the global. So it is up to the user to do this. And then we created the data set with the global extent and type. And we can create two types of data, species data or mesh data. Hence the name of the library, Open Particle and Mesh data. And this example shows how to create species data, but it's identical to mesh. So you create a species, you give it a name in the record. In this case is position X. You reset it and you call store chunk, and at this point the pointer has been appended into this dump vector, and it awaits to be written to disk. Actually, I'm not sure if at this point it already starts writing to disk and flush just waits to be completed. I don't remember exactly from the documentation of the library. But this is how you prepare the data to be stored to disk in parallel I/O. So this is all. If we if you want to write in memory, so-called streaming, we only need to change the extension to SST, and this is forgot the name, stage transmission, and we have to give some extra parameters to this series object, which is this so-called variable base, but it's some detail. We can specify data transport. This is wide area network. If we want for the simulation to wait until we flush everything to disk before continuing, in this case we say no. So it's non-blocking, which means the simulation will not be affected by the writing to disk once this data has been appended into this global vector. We can have a queue, how many of these iterations to be saved into memory. I put 2 because when you write to memory and you have one reader, which is your visualization, then that's your consumer. And if you want to have an extra consumer, you have to either stop your visualization, maybe you don't want that, or you can increase the queue. And why do you want an extra consumer? You can actually grab this stream and also write it to disk using OpenPMD pipe binary, which comes with the library. So In that way, if the simulation writes only memory and it stops, then the evolution of your simulation is lost. So, but if you grab the stream and write it to disk with an extra read consumer, then it can be restarted from there. And of course, when this queue is finished, you can just, when this queue piles up, you can discard the older iterations. So now parallel read from disk is also called restore from checkpoint. Now the data on disk is already joined from all the MPI ranks. So this helps us not only visualize it, so we don't have to join it up as in a post process, but now because it's joined, we can now read it back any way we want. So we don't, so the data that each MPI rank wrote to disk in parallel with parallel IO doesn't necessarily need to read it back in the same amount. So we can reassign now back the data to each MPI rank the way we want. And this is basically the, let's say, beginning of particle load balancing. So when we read back from disk, we can assign a non-uniform particle load to each MPI rank. A non-uniform domain to each MPI rank. And this gives us the possibility to have a uniform particle load. So initially, without, let's say, this option of load balancing, each MPI rank has equal share of the domain. But in particle space, this is not uniform because each cell can have a different number of particles. And this particle load can be different. So, but this means that also each MPI rank will do a different amount of work. So if you want to redistribute the amount of work between MPI ranks, we have to redistribute the number of particles between the ranks, which means that each rank will have to work on a variable domain size. And this can be achieved with this parallel IO because the data is already joined on disk. And now when we read back, we can just reassign a different number of cells to each MPI rank so that we have uniform particle distribution. And how does parallel read from disk look like? We have the series. Now the axis is red linear. In the write mode, it was axis was like write. And we have to know the local extent and offset before we start reading. So it's up to the user to read this information before. And we create the same objects for species. But now we don't use store chunk, we use load chunk. And this gives us let's say the pointer to the data. And in this, okay, this is number of particles, but if we go to for each particle, then we have the record component, which is the x position and the 3 velocities. we know the extent because the way we wrote it in the first place, and we call load chunk for each record, and we accumulate all these pointers, and when we're done, we close the iteration, and in this case, for reading, flash is automatic. And at this point, all this data is being read from disk at once to minimize the reading time and to maximize the read throughput. And if you want to parallel read, to read with parallel I/O from memory, to be used, for example, for institute visualization, we can do this, let's say, in a different in a different language. For example, in this case, is Python. For example, for our plotting scripts. And I'm showing here an example of a made up, let's say, case where you have a source in the middle, starting in empty vacuum, and the particle load across MPI ranks has this shape. And we save this checkpoint, and we continue. So save to disk and continue from disk with this option of particle load balancing. And this is the next, let's say, checkpoint after this one. And we can see that it's now the particles are, say, uniformly distributed to all MPI ranks, except for the last one, because you can't split a cell in half. So some particles the last rank rows have a bit less, but in the future we will fix this. So because if we increase number of ranks, then it might be that the last MPI rank has no particles at all because they have been redistributed to the previous ones. But this will be fixed in future say releases of this branch of the code. Yeah, so this work has been done under Plasma-PEPSC project, and these are the partners. And now I will show you on Carolina. Sorry. A small demonstration how I'll increase the font size just a second. How to use this new say branch with parallel I/O. If you write just BIT1 executable, you will get sorry. You will get instructions on how to use the executable. So-called BIT1 usage. So how you can run from scratch. This is how you run with streaming activated. Yeah, using this streaming option. This is the original restore from the original way of using restore from disk, but you can restore from disk and continue the simulation with streaming. You can restore from disk with load balancing, and you can restore also from disk with load balancing and continue with streaming. How do you, and you can also switch between, original serial and parallel IO with just one parameter in the input file. And I will show it to you now. You just switch this original dump number. If you put 0, it uses ASCII as explained in the BIT1 manual. If you put 1, uses the binary original serial IO binary from BIT1. If you put 2, it uses the parallel IO. So if I switch here to 1, it will save the original BIT1 files. If I put here 2, it will save in parallel IO in binary pack 4, in this case, file. And with one input file, you can switch between the two. So you can start a simulation and run in original BIT1 file. You can continue from there and save in parallel IO. And then you can save back to original IO. So it's easily interchangeable between the two modes of writing to disk. How does this look on disk? So this binary pack 4, actually it creates one directory. This is a directory. We'll go inside it. It comprises of several files. The data is actually in this file. And there's some other metadata. There's a file called profiling, which tells us how the data was written to disk and what was the byte rate, I think, number of bytes. Is this all? So some IO info is being dumped in this file. I have a few more minutes. I can show you how I read from disk. So I have a Python script called stats. So I import here the OpenPMD API for Python. And I read, for example, meshes that I saved during the simulation, position, density, and I call this a load chunk. And then I start using it in my plotting code script. And this is actually the main that is the plotting function, but here actually we choose we can read streaming or we can read from disk. And if you read from disk, we only want to see the last iteration. That's why I made extra opening here. But we just read each iteration, and okay, we take the last one, and when we plot it and we close the series. If it's streaming, we have to give some extra parameters like data transport. But we read each iteration that we receive in memory, and then we plot it. So if I want to see, for example, this data, I just call this and put the BP4 extension. And I see, for example, some statistics about the simulation. So I have the density profile, but then I also plot some numerical stability graphs like plasma frequency times time step, and I want it to be below 0.2. So this is the no-go region. So I see that in this case, it's good. Then I plot number of particles per cell just to see that how it goes. This is the time step over the Debye length. It should be lower than 1. So here we are good. But what we see here that particles with 5 times thermal energy will cross more than one cell in a time step. So this is bad here. So here we have to reduce the time step of the simulation to be numerical accurate. And so visualization can visualization can be used for debugging. Yeah. If you want to see profiles, of course, I just changed the script. So I see some profiles. Yeah. I can go to the example of time is up. Okay, quickly. Of the that you had yesterday, which is the beam, which I had the liberty to run with parallel I/O, and I can call the data. I ran for like I say 32 movie steps, and you can see that it's numerical stable. So you see here a density profile and all of these values of omega. So plasma frequency times time step is well below 0.2. Cell size over the Debye length is below 1. And the fastest particles do not cross. They are the fastest, but let's say some of the fastest particles will not cross one cell in one time step. So it's numerical stable. And you see also here the particle load across MPI ranks. It's uniform a priori because simulation starts with not with an empty system, but with a filled-in system. Yes. Okay. Thank you. This is all. Any questions?
I had a question, just a curiosity regarding the parallel writing, because have you mentioned that if you use the HDF5 you would get by worse performances, but have you compared the performance in writing?
Not
case?
myself, no, but this is I think explained in the documentation of OpenPMD that with HDF5 you will, in some situations, you get less performance than with binary pack of ADIOS 2. Yeah.
How much? An order of magnitude or less? Just to know.
Yes. I think that is the case. Yes. So people were switching from HDF5 to ADIOS 2 because it was much more performant. Yeah.
Okay. Thanks.
You can come here, David.
Let's try this microphone.
No?
This one is working. This one should be working.
Okay, both work. Yeah. Okay, thank you very much, Stefan. I have two questions. I mean, is this done for GPU version of the code or it's a CPU version?
This is the CPU version.
CPU version of the code. And could it be done also transported easily to GPU version?
Yes, so I had this discussion with Jeremy before the meeting, and I postponed it for after the training because I wish to merge this work with the new BIT1 source code from the repository. And after that is done, then I will merge with the GPU branch and to have everything in one place. Yeah.
And now about the diagnostics, I mean, is this same diagnostic as the, let's say, a conventional BIT1? For instance, BIT1 has static diagnostics, time-dependent diagnostics for profiles, distribution, spectroscopy. So how is it same here or just?
So at the moment, I have implemented for slow equal 1.
Okay, so static.
So you can see here the functions that are that being slow equal 0 and slow equal 1. So plasma profiles. Okay.
And probably you said then you don't need
PDFs.
movie file because it's, as I understand, it's overwrites. So it's not overwriting, but it's just adding.
So I have also movie file, and what you saw actually the plots from before are from the movie files.
Okay, so it has almost same functionality as.
Almost, but it's not all of it.
Okay.
It's work in progress. Yeah.
Okay.
And also what I did not implement yet is the units of the physical quantities, and maybe we can reduce the size of the data by having some multiplication factor that can be saved separately. Yeah, and to increase precision. Yeah.
Okay, I mean, the one point, very important point, which you didn't mention is that actually when you have, let's say, 1 million CPU hours minimum time we run, we don't care about how many faster seconds will be saved. The problem is simply if you go above 20,000 cores, the original version does not work. You need a dedicated like this one's, let's say, approach. So it's a must go update. So it's not just speed, because first question would come if you are running 1 month, and then is any difference if it's 20 second or half second? Of course not, but the problem is it will simply corrupt it. So we made many tests, and so this is the most important point, that if you go for really exascale or even just very high massively parallel, so above 20,000, so at least 40,000 I was getting corrupted output. So it means you need this. So thank you very much for this.
Thank you, David.
Thanks. I think now
I have a question from the audience.
So thank you for your talk. I had a question about the slide on the where you showed the parallel reads with the data. Yeah, this one, the in situ visualization.
Yeah.
It seems the potential curves are pretty different with and without load balancing. Do you have any insight on this? It's just RNG or?
So it's just one. I think it's one extra movie step later, the one with restore, because I had to read from the previous one and wait for a next checkpoint to save it to visualize it.
Right. Okay. Excellent.
So they're not identical in time, just 1 or 2 movie steps apart. Yeah, and the potential is it changes in time, it fluctuates. So you will not have you have let's say varying profiles in between movie steps. Yeah.
Okay. Thanks.
Yeah, so I had a question that usually when you do parallel programming, you look at strong and weak scaling. Are those plots you can make for parallel I/O as well?
For BIT1, it's not necessary because it's not the write throughput is not a bottleneck for BIT1. BIT1 needed only the ability to have more MPI ranks working together and writing to disk. And this is achieved by not writing all of them to disk, but some of them will communicate through MPI, and a smaller number will actually write to disk, and this actually enables BIT1 to use much more MPI ranks. If you wish to know more about how fast this library can go, they have good publications on the efficiency of these libraries, parallel I/O, and how fast they can get on really powerful HPCs.
So what's the percentage that the I/O takes in terms of let's say a runtime?
Less than 0.1%, I'd say, in case of BIT1. Yeah.
All right, thanks. Yeah.
Thank you. You can.
Like coffee break now.